Yo, 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 what's up, everybody? Welcome back. Today we are working on drawing anything with, in like a Linux machine with no dependencies. So we could call it raw dogging Linux graphics, if you will. And the context here is that my parents came over one time and they were like looking at my walls and they were like, "You have no art and your soul is gonna die." And I was like, "That's true." And so I should fix that maybe someday. And I looked in like my box of stuff and I had a roll of these like LEDs that I bought like 10 years ago, right? And I never did anything with them. But I kind of had this idea where it would be kind of fun to like buy like the cheapest computer I can find, like a $2 microcontroller. Tape it to the wall and tape all the LEDs on the wall too, and like render some stuff on there. It'd be kind of fun. And then I was looking at that, I was like thinking about it. I was like, probably a microcontroller isn't like fast enough to do any like real 3D work. And so then obviously, the next thought is, what if we just made a GPU? Right? Then we could do all the 3D acceleration in this like other chip and use that chip to drive this like display of LEDs on the wall. And then on there, we could do stuff like, I don't know, like write some 3D games to run on this like piece of shit attached to my wall. And then it could display whatever we want. And that's the solution to the art problem, right? Obviously, because then you only just need one big wall full of LEDs. And so we are extremely far from understanding what the hell that means, right? If I'm like, I want to make a GPU, I don't know where to start there, right? What do I know right now? I know that I have like a monitor attached to my computer, right? He's like sitting here on his like little monitor stand. He's got a wire, and he's going into like this like graphics card sitting in my machine, right? And this thing has like some access to like DRM, kind of, right? This is kind of like my current mental model, and like also like CPU talks to this thing, right? And all of this kind of is like where my like understanding of this like ends. I kind of understand that like CPU asks GPU to draw stuff. How? Well, when I work with the GPU, I know that I'm like over here in like user space and I write like open GL. And I kind of know that like in here is this like cloud of stuff, right? And the cloud of stuff is kind of like running in like on the CPU in the kernel and in user space, right? So there's like Mesa, I've heard about Mesa, like libgl, libegl. These are all like words I've heard. Vulkan. And then like in like the kernel, I've heard words like DRM and like kernel mode setting. And like, there's like a lot of words in here. And I kind of feel like if I were to ever make a graphics card, I feel like to design a thing that works well, I would have to understand kind of like all of this stuff. At the very least, like maybe not understand all of that stuff really well, but maybe like kind of at least understand what goes on like here, right? That's like really important. And so the goal for today is to start on this trek of I kind of think that the project goal should be write a Linux graphics driver that renders stuff with 3D acceleration on my host machine through some custom API. That's kind of like the end goal of the project, because then we can like prove to ourselves that we kind of understand how the whole system works. Maybe we write like an OpenGL driver to go with it, and so that we can like understand what is actually required from the hardware versus what's required from the software. And so today's task is step one of that, which is just draw anything at all. We did a bunch of research in happy hours a couple weeks ago. If you want to check out those VODs, they're archived on Patreon or in YouTube member streams. I think they're called something like Linux Graphics Deep Dive or something. But the summary of that is like this like massive chunk of text on the right that I'm going to be referencing. So we kind of like we're looking at all this stuff in the middle and trying to understand what is going on in here. And my current understanding is basically this picture. This picture from this like sick LWN article called Linux graphics stack in a nutshell. And basically, they kind of explain the whole pipeline of like what is exposed to user space. So as far as I understand, for like the very basic, just like I want to put pixels on the screen, you have. Let's start at the end. Like you have like a cable that's going to your monitor, right? And if you were to imagine like the world's simple, like the simplest case of this is like a CRT monitor from back in the day, which we don't really use that much anymore, right? But you have like the CRT monitor, and he's got like this like big chamber back here, right? This kind of look like something like this, right? Like I don't know. And in here, there's like a gun, and the gun is like kind of firing onto like this surface. I think it's like this like surface that lights up when you shoot it with an electron beam. I think is how CRTs work. And so there's this gun that's kind of like going like this, kind of like wiggling back and forth, really really fast. It's a phosphorescent film. Yeah, that sounds right. That sounds right. And so the simplest case of this is you have like this wire that goes out here, and basically like at any point in time, the gun is just shooting out like how strong the signal on this wire is. And so if you time the highs and lows of what's on the wire with where the gun is on the screen, you can kind of like draw a picture. You can draw a picture. And so there is like the encoder part of this, right? The encoder is like this piece of hardware. I assume this is kind of like all like hand wavy, right? I don't really know what the fuck I'm talking about, but if I understand right, the encoder is kind of saying like, okay, so we have to take some stuff that we want to draw, and we have to turn that into like voltage levels on the connector. And so my understanding is that is what this DAC encoder is for. Then behind that is this like CRTC module, which is called like a cathode ray tube controller. So because we're talking about this like old case back then, the name is left over. But in general, my understanding of this thing is it's like set up for like parameters of how you are going to draw what you have in like a buffer. So somewhere you're going to have like a buffer of stuff, and you might want to draw like, you know, this section of it on the screen. And so like the CRTC kind of says like, okay, so maybe this is like a 640 by 480 buffer, but your monitor is like 1280 by 1024. And so like you might have to like scale this up. You might want to iterate these pixels like twice per, or like once every 2 clock signals instead of like, you know, once per clock signal, stuff like that. I think that's this guy's job, is to kind of say like, there's like some stuff on the screen, and let me figure out how I want to display that stuff, how I want to feed that stuff into the encoder. And then behind there are these like planes, if I understand correctly. So maybe we start from the other side now. From the other side, there are these things called like, you know, if I just have like a picture that I want to draw, right? This is like something in memory, right? And this is just going to be like pixels on this thing in some way, right? We attach a set of pixels to a frame buffer, and a frame buffer is maybe multiple collections of pixels, because like if you have pixels kind of split as like you have like your Y buffer and then like a UV buffer over here for like luminance and color, these might be stored in like separate locations of memory. So a frame buffer allows you to like tie those two things together. And then the last piece is planes. So you can kind of take multiple buffers and like stack them on top of each other and say, could you draw all these buffers at once? That's kind of my understanding of this pipeline, right? So pixel data, frame buffer, planes, monitor setup, you know, signal setup, actual display device. That's my current understanding. And so let's just kind of see if we can like figure out how that shit works. We encountered a lot of words in our research, so I'm just going to maybe quickly ram them out now. Don't feel like you have to remember everything, because I'm sure that we'll come across them later, but just that you have like, oh, I've heard those letters before. So my understanding is that like GPU driver implements this thing called DRM, which I think stands for direct rendering management, maybe? DRM, what does it stand for? Shut the fuck up. Not digital right management, Linux. Direct rendering management. I was close. So this is kind of like, as far as I understand, like essentially just like a way to manage resources on a graphics card, right? And it gets like more complex than that, but kind of like just I have like memory on the graphics card, right? And in the same way that when you type malloc in your code and you want to get like a chunk of physical memory, but the kernel kind of like maps that memory in a way where it's kind of transparent to you, and all you have to do is be like, get me some memory please, even though it's a global resource, you can kind of like access it with unprivileged access. I think DRM is like a similar mechanism where you're like, I have some GPU memory and I would like to get some of that please, but that process has some and that process has some, and so I'd like someone that isn't used by either of those type shit. And like maybe like while I'm active, maybe like that somebody else's GPU memory isn't really in use right now. You can like page that out to disk and page it back. That's what I understand. My understanding of it. Maybe I'm wrong. We'll find out. Then there's this thing called gem, which I think is like a kind of user space API to access uh, GPU resources, I think. Then there's like this thing Mesa, which is like an OpenGL implementation, and he sits on top of DRM and GEM, and he's like kind of your user space graphics stuff. I don't really understand very well. We'll figure that out when we get there. libdrm is very important. So when I talk about raw dogging Linux graphics here, I'm going to be cheating a very slight amount. Usually I would say really no libraries, right? Only the Linux kernel. However, in the case of graphics drivers, this user land interface is part of this like kernel development guide. I think this is from the kernel itself. They have this note about graphics devices where these things are really complex pieces of hardware with user space and kernel by necessity having to work together really closely, right? Because you don't want to do all of the work for your graphics driver in the kernel space because that's expensive and like risky. You would like to do more, like it's so complex that you want to push a bunch of stuff into user space. And so because of that, the interfaces for rendering and mode setting must be extremely wide and flexible, and it is almost always impossible to precisely define them for every possible corner case. This in turn makes it practically infeasible to differentiate between behavior that is required by user space and but must not be changed toward regressions and behavior which is only an accidental artifact of the current implementation, right? So usually when you're working with the Linux kernel APIs, you kind of have this guarantee that like if you use the APIs like correctly, like nothing will change in the future, and if they have to make a breaking API change, they will just like make like function 2, but they'll make a new version of it, right? But in the case of graphics, it's so complex that they're kind of saying like, look, we don't know if this is like a mistake or if it's being used right now. So the only way that we can fucking tell is if you have a user space implementation of this that we can review alongside. And so a lot of this code for like interacting with Linux driver, GPU driver stuff ends up in libdrm. That's my understanding. And so we will use libdrm, but we will try not to use anything else. And I think that's really it. Okay. Kernel mode setting is also important. So, your monitor, he has like, he's like, you know, what's 1080p usually, right? But you can ask your monitor to go into like 480p mode, right? And so like how do we manage this? Well, there's like this standard interface in the kernel that says, well, my monitor is plugged into my graphics card, and my graphics card is going to want to send commands over to the monitor to like set up its display stuff. Basically anything about like monitor parameters is called like mode setting, and before this was done like entirely in user space, but was like a total fucking disaster if I remember correctly. And so they kind of like put all of this stuff in the kernel drivers and just expose like this common interface called kernel mode setting. Lots of like words and information coming at us at once now, I understand, but I'm just trying to give you the background that I have so that when we start digging in more, you guys aren't just like completely out to lunch, maybe just like a little bit confused, and we'll probably try to revisit these things later. So long fucking intro, understood, but worth it, I think, because otherwise we won't be able to do anything. Okay. So, I think that what I want to start with, will this VOD be on YouTube? Yes, it will. What I want to start with is like, let's just try to figure out anything about our GPU. Let's try to figure out anything. Oh, I completely missed another segment of this. Okay. So I have set up a virtual machine where I can, I have a testing environment where I can use this window manager. Hold on. Let me log in. I fucked up login. Root. Where I can launch this window manager Weston, which is like the Wayland reference window manager, right? And so what the only reason I've set this up is because I wanted to prove to myself that we have dev DRI access set up in here, right? So here we have like a virtual machine playground where we can try to interface with the graphics directly, and we had to do this because I don't have a stream PC, right? So I can't really just like swap into a virtual terminal. I need to have graphics up on my main machine to like so you guys can see stuff. So this is like the workaround for now. This graphics card that we have in here right now is the QEMU QXL graphics card, I think. And he doesn't implement any 3D APIs, but we will be using this as a starting point because I didn't really know how to configure QEMU to do what I wanted. There is a like 3D QEMU pass-through thing, And we might look into that later. I am not sure. I'm not sure. And so, how is this virtual machine set up? Is kind of interesting. Kill all Weston. Get me out of here, please. Thank you. Actually, I guess I just want to just get out of this completely. We have this GPU testing environment where I am basically building this project called buildroot, which basically says like, hey, I want like a Linux file system with some stuff on it. I would like to compile all that stuff, please. And this is kind of just like, it kind of packages up a bunch of build rules for a bunch of different pieces of software, which is pretty sick actually. So like if I go into like my buildroot folder and I like make menu config, there's like all sorts of stuff in here, right? So if I wanted to install like, I don't know, Firefox, is that probably too extreme? Maybe something more like tar. Bad example. Can we just look through maybe system configuration? No. Where are the programs? If I look for WL root here. So okay, here is just like a bunch of packages that it allows you to install, right? So if I want to install, you know, SDB, go ahead. If I want to install OpenJPEG, like I just click this button, it builds it, installs it for me. And so this is kind of a way for you to like configure a sysroot without having to like pull in like all of Ubuntu or something, right? So we're using this to generate our user space. And then we are building a Linux kernel ourselves, and I have these configs set up where I basically just kind of like modified both of these until I got to the point where something kind of worked. So if you guys want to check that out ever, those will be on the GitHub at GPU testing environment. And I just like committed the configs that I'm using for these here. Yeah, okay. So I have Weston, I have another thing, WL roots. This is like another like Wayland abstraction library that kind of interfaces with initializing GPU devices directly, and they have this program tinywl, which is like their minimal example of using their library. So we have a couple examples of people who can like initialize a graphics driver, and we are going to be maybe referencing these, as well as referencing this blog post. I think is going to be the real winner here. The real winner. So yeah, okay. So the goal is let's just try to get any piece of information out, any piece of info. And I guess we'll reset the time, and we'll just say that the intro is even longer. Long ass intro. Okay, so this diagram models like the user space API relatively closely, I think. So my understanding is like we first want to do like mode setting. We want to set up the display to like set some form of parameters. Then we are probably going to use that information to create a pixel buffer that we're going to render stuff into, then set up all of this stuff and hopefully get some output. Hand wavy. And I think I just want to follow this guy's information a little bit. So he says, let's start by opening up a handle to the DRM driver device. So if we go back into our little test environment, am I going to be doing this zig? Yeah, I think so. Why not? And I actually set up an SSH name in here, which is pretty sick. So I think I can, if I go in here and I call udhcpc to get an IP address on ENP0s3, we have an IP at 10.023. So I should be able to, which in my run script, I've port forwarded from localhost 5555 to port 22. So I think if I do SSH local host 5555, and then I probably want to SSH as root because we don't have users on this machine. What do you fucking take me for? There we go. We are in. So like we are just like a little proof. I type Weston over here. That starts up the window manager here, and then I control C. It's gone. I assume that you use GFX APIs like Vulkan or OpenGL. Yes, but those are built on top. So Vulkan and OpenGL are kind of like if I understand correctly, which I probably don't. They're like, I would like to do some 3D rendering with the card, right? But they don't kind of enforce things like how am I going to take the things I rendered and put them on the screen, right? You kind of need, well, they do. I guess like OpenGL has like GL. I can't remember. I think that their GL viewport, I guess, is kind of what I'm thinking. So there is something along those lines. But I think that before you open those things, you need to like initialize kind of like the backend correctly. I think some people use libegl for this, which I think kind of does the same thing, where you can kind of say, depending on what environment you're running on, right? If I'm like raw in this window, the way that I get an OpenGL context is going to be very different than the way I get an OpenGL context if I'm like in a Wayland window manager already. GLFW, yeah, so GLFW will ask someone under the hood a little bit lower. That's what EGL-EGLX is the glue between OpenGL and the windowing system. I'm under the impression that EGL works without a windowing system as well. I could be wrong about that, but I'm pretty sure it does. GLX is like the X server has done all of this DRM initialization, and I would like to ask the X server for a handle to that. Then there's like stuff about like buffer transfer between different processes that's kind of handled maybe through those. Not entirely sure. Windowing should have been in quotes too. Yeah. Okay. So let's try to write a program that will call use libdrm to do something. So we should have libdrm sitting somewhere. I think that our build root kind of downloads all of our projects and gets all of their source code in here. So, and when it compiles them, it puts them in this like staging folder. So everything that's available on our target virtual machine should be available in this folder. So if I want to use Zig to do stuff with libdrm, I guess we are probably going to have to point it to this stuff somehow. But we will figure that out in a second. Let's start by just compiling a program and sticking it on the disk somewhere and seeing if we can do something interesting with it. So let's say test app. And let's get Zig in our environment. So I think that usually I hack my shell.nix to have Zig 013 available to us. So let's just kind of pull that hack back. Oh, I already have the hack there actually. I just don't have this stuff. All right. So I think if I type nix shell here, I should get Zig up and running. EGL supports a ridiculous amount of windowing systems, at least as far as I know. Yeah, that's my understanding as well. I was looking at the source code a little bit. I was trying not to cheat too much, but I was making sure that like indexing was working correctly. And I think that if we go into source EGL here, we see like the direct rendering interface has like X11, DRI3, Wayland, Surface List, DRM, Android. Like, you know, there's a lot of stuff in here. Okay, what was I trying to do? I was trying to make some sort of test app. So can we do like make dir source is how you usually do this. And then you like main zig and then function main void. And let's just do like a print stud debug print hello world. Okay, and let's just kind of make sure that if we put this on our virtual machine, we get something. Right, so let's do a, do we want to set up a build.zig? Probably, right? It seems like we are going to want one. So const stud is equal to import std, and then we're gonna like b dot, what do you usually get? You need like standard target options and standard optimize options. There we go. These are the usual, and then you do b dot add executable. Yeah. With root source file is source mainzig. Okay. Target is equal to target. Opt is equal to opt. And then they usually give it a name as well. So we'll call this a test app. Okay, and then b install artifact exe. Okay, this is our little testing environment, and this will be useful later when we try to link against like libdrm and shit. He doesn't like that because it's called optimize in here, not opt. Am I late to the party? No more dsphero. Yeah, I think that I kind of accomplished what I wanted to accomplish there. So I kind of figured I would like to move on to something I'm like this is kind of more the project that I really wanted to be working on, and the dSphere was supposed to be a tide me over until I was ready to work on this. Okay, so we have a test app, and let's just take a peek here. So it's not a dynamic executable. Great, really good for us. So if we kind of take this and we slap it in our overlay here, and we rebuild our file system. So it's make-j9. This will basically rerun the kernel build and the build root build, and this overlay file folder is like attached to the file system that build root generates. So build root is generating like an ext2 file system image that we are pulling in and mounting at dev VDA with this command here. So yeah, build root images rootfs ext2, and build root in its config has something. He has a overlay thing. Yeah, and so we can say like, please include this stuff in the file system. I'm seeing an error here that I haven't seen before, which is not great. Could not allocate block in ext2 file system while writing file Weston content protection. Maybe you need to increase the maximum size. Okay, let's take a look at that. We could just maybe double this for now. It's possible that I accidentally added some stuff and I didn't notice that it was broken. So we'll give him a sec. Let's try one more time. Better, nice. Are you going to implement a graphics driver? I think that is the goal for this project. Yes, that is what I want. That is what I want to end up with. Okay, so we should have at user bin test app a legal instruction. So we are already immediately fucked. That's kind of fun. Okay, so we probably want to run our Zig build. Actually, let's leave this open in the background. And then we will try to SCP stuff in. Maybe we'll try it that way. So let's see here. Let's try to like Zig build help. How do I specify targets again? It's like d target equals x86 64 Linux. Oh, but that's kind of where we are right now, right? Surely we were already on that. But let's see. Zig out bin test app to localhost root at localhost 5555. How do you do SCP with port specification? Oh, you specify port directly here. So SCP 5555 given our source, and our target is going to be localhost root at localhost. Okay. Okay, that did jack shit. Damn, I was kind of hoping this SCP would get me what I wanted. Oh, so that's why that first SCP worked. It could be that my SSHD doesn't do what I want it to. Is it possible that your QEMU guess is a different arch by mistake? Could be. I mean, we could check if we did like file not found, but if we did, if we go into our build root build and we look at like anything that's in bin, we can do file busybox. So this is a ELF 64-bit LSB Pi executable, x86-64. Okay, so what if we did a quick test instead in C? Okay. And we can try to bisect problems here. So let's do like printf hello world. And we can't use our host GCC. Instead, we will use the build root GCC. So this kind of like sets up a bunch of like flags to match kind of like where like libraries are, and not use like the system libraries, and like whatever configuration like is set for this, the GCC are kind of like bundled with GCC. Try disabling AVX SSE SSD2 maybe. Yeah, I think that's likely. I think that's likely the problem. In fact, we could probably test that by, we could probably improve the QEMU command lines to use like KVM and CPU host, and I think that might improve stuff. That's a good guess. That's a good guess. Because I think that we saw when we were working with the Linux kernel driver that like debug formatting was using some like AVX registers to like cache stuff just cause like it could, or maybe some floating point registers. But we'll see. Okay, so if we do like, let's put this in the overlay, test C, and do this. So that compiled okay. And if we do make and then run again, because unfortunately the SCP path is not doing what I wanted to do. So it could be that dropbear, the SSH server I'm running in the build root, doesn't support SCP or something, or I have to like configure it somehow and I haven't done that. So for now, we will just do it the slow way. We will do it the slow way. So we should have a test C now, and that says hello world. Okay, so that's a good clue. A good clue. I guess we could even check. Is there like a CPU like cat? We can cat proc CPU info, and we can see if he does not have things like AVX and stuff. I don't see SSE or AVX, which might be relevant, and so we could try. We could try. I think it's like enable KVM and CPU host, and that should improve the emulation. Okay, there we go. No AVX, but SC2 is the NCB info. Oh, okay, I just wasn't looking close enough. Nice. But if I enable KVM, enable more CPU flags, then we get hello world printed. So our Zig build is now working correctly. Big win for us. Big win for us. And so I guess now the next thing to do, by the way, you should be able to share a directory between host and window manager so you don't have to SCP the thing every time. Yeah, I was hoping that I could just use SSH because I didn't want to set up like any of those like more complex versions, but I guess this are like QEMU shared directory. Maybe there's like already something. I don't want to look this up. Vert FS. Yeah, I assume that there's going to be some sort of driver that I'm going to have to look up. Yeah, I'm just not going to do this right now. We're going to do it the slow way of rebundling our file system image every time, just to avoid what is already going to be complex. We have enough stuff to deal with today. Let's not make more problems for ourselves. Okay, let's see if we can figure out how to like link libdrm here. So we're probably going to do like some sort of like C import. And it's going to be like C include probably libdrm.h. Probably. Does this guy kind of say what he's doing here? Well, first he opens the thing, but then he calls drm get resources, which I guess let's try to figure out where that is. So that's in build root, build libdrm. Nice. Include. Nice. DRM. Oh, it's drm.h. drm.h. And does this like forward the other includes on? Maybe there's mode. DRM mode.h also sounds promising. Resources? No. DRM mode get resources. Let's do this. Build root. Staging. User include libdrm. Rep drm mode dot. Why does that not exist? Why does that not exist? This is not a good sign. DRM mode get resources comes from xf86 DRM, which is not in here. xf86 drm.h. Okay. Get resources, not here, but I think I saw like another. Here it is. Here it is. So I don't know why this is tied to XF86. I don't know what this is. Oh, maybe this is, we don't need libDRM for these. Maybe these come directly from the Linux kernel. That's a possibility. That's a possibility. Can we look at like source Linux? No. Nope. Not clear. Not clear to me at all. But I guess we'll find out. XF86 DRM is the generic DRM. Ah, gotcha. But I wonder what XF86 stands for. What does this mean? Oh, this does come from libDRM. I just missed it. And they don't really say what it is. But okay. Sure. Whatever. So that means that in our thing here, we want XF86 DRM and XF86 DRM mode. I think were the two things we saw. Can we ask Zig build to not use our system includes? I think it's possible. I just don't really know how. It must be part of the like add executable things. DRM as in the stuff against piracy? Piracy? No. It's a different DRM. Different DRM. It stands for direct rendering management, I think. So does this thing have a way to be like, don't use my system stuff? I don't see that here, but then sometimes there's stuff on like the root module that it comes back as well. So compile has like root module. And link libcpp. Not really what I'm looking for. I guess maybe it's related to like the resolved target. I think maybe the target sometimes, because like cross compiling is like well supported. So what are my like, can I check what options we have for target strings? Like, am I supposed to do like unknown, like XF86 64 unknown Linux or something? Maybe. Zig build list targets. Bump. Targets. Zig targets. Here we go. Sick. Okay. So XF86 Linux. Okay, let's just try. Okay, if I build this now, he probably should succeed. Yeah, he does succeed because he finds XF86 DRM, and I kind of want him to not succeed. That's kind of my problem, is because he's leveraging some system includes that I don't know about. Can I set the sysroot to the build root generated one? Ooh, maybe? Maybe. I want to try first, seeing if this still succeeds. If I do target is equal to XF8664, like Linux GNU. If I specify this manually, oh, sorry, x8664. I had the F stuck in my head. Yes, that works fine too, which seems kind of bad. Arch OS. So there's Linux, freestanding, ABI, GNU, and then libc is supported on all of these guys. Yeah, that's a little annoying. A little annoying, and I don't know how to disable it. So do we skip this for now and just work in C? That might be the play. Just because I don't want to spend my time on this today. We already have enough to cover, and I think debugging Zig is going to make my life harder rather than easier. So we'll just do it in C for today. For today, and maybe I'll figure it out in happy hour or something. Okay, back to trying to actually get some information. So let's just start by opening dev DRI card 0. Okay, which I think means like, is it una std here? Man to open. It's in FCNTL. And he expects some flags here, which, read write seems reasonable to me. And then we want to include xf86 drm.h. And okay. Does this work? GCC. DRM.h, no such file or directory. So I think that now let's include our overlay, maybe iSystem. And this comes from build root, staging, user include, libdrm. There we go. All right. Now let us try calling this DRM mode get resources. And he just calls out on FD. And let's see if we can look up DRM mode get resources. Does somebody tell me what this does somewhere? Man pages? Okay, sure. So this is going to be in like the libdrm docs. Allocates and populates and returns DRM mode res structure containing information about the current display configuration. The structure contains the following fields. So the number of frame buffers, the number of monitor control objects, number of connectors and encoders. Nice. Okay. So can we just like look at these? So where my pointer, how do I know? Oh, count. All these things have count. So let's just start with like checking the return value of this thing, which is going to be a null on failure. So we'll say we need to specify this type. Mode resources, I guess. And then we will do like printf num crtcs is this. Oops, I don't know why I put a space there. Brain's not on. And this is going to be like count crtcs. We should fix up our indexing in a second here, but let's just try first and then we'll figure it out after. Implicit function declaration. So that's not good. That's not good at all. This does want me to include this as well. And then we are missing DRM get resources. We need to L DRM. Sick. Okay, let's fix our indexing. So we'll just kind of like slap this guy into a file here. And then hopefully, oh God, what's happening? He's still not happy. Probably because this needs to be a absolute path, maybe. Test app here, like this. And then we also need user include, probably. Okay, let's try that. Still not happy. I thought Clang D works this way. So this stuff should get resolved by the second command here. Clang D config file. I think that there's a way to do this. I'm pretty sure. Oh, right. Did we saw this yesterday or the day before when we were looking at our GUI stuff here? We added this Clang D file that had compile flags. That was what it was. We fucked up. We don't just write them raw. we write this like this. So what was our I system? Like this. Sorry, I know this is kind of boring shit, but it will speed up the rest of our lives immensely. So I guess here we kind of just do this. I think that should do it. Much better, much better, much better, much better. Okay, let's build our thing and then test if we see something reasonable. Oh my god, this is slow as shit. But maybe it is a pain we have to live with. For QEMU, it should be 2. Maybe 1. Maybe run. Maybe 1, sorry. Run.sh. Root. And can we run, what is it, test app? No, test C. There we go. Num CRTC is 4. Num CRTC is 4. So I guess we didn't do any real error checking here. So let's maybe do that. So man to open. This guy returns, I think, negative on failure. -1 is returned. Yep. So if fd is less than 0, fprintf ser failed to open card. But I'm pretty sure that this was fine. Is this how this works? Fprintf, yeah. And then return. And return, I guess, fd. Sure. Or -1 is fine. It's fine by me. Or return 1, I guess, is how you're supposed to do this. That makes more sense. And then if mode resources is equal to null, then failed to get resources. But it sounds like we didn't. And can we maybe like log a couple other things in here? We might as well just log everything. We might as well look at the encoders and the FBs as well. Might as well. And this is encoders and FBs. All right. All right, and then I also want to fix up our makefile a little bit to bundle this thing automatically. So let's do something like we get overlay. What was it? Overlay user bin test C is defined by test app test C, right? And here we call this command, except this is now not // anywhere. And then I think this should work. And then we'll make the build root command depend on overlay user bin test C. And then if I do make build root, everything should kind of work for free. But it doesn't work because test C needs to now be in test app. Boom, 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 boom. All right. 4, I think I misunderstood what CRTCs are then. I mean, me too, me too. 4 seems high to me. I'm not gonna lie. Not gonna lie. But we shall see. So he has no frame buffers, 4 encoders, 4 CRTCs. Surprising. Surprising, surprising, surprising. So maybe these are maybe configuration, like maybe each one of the CRTCs is like a different mode. Maybe. Maybe. Let's see if this says anything. The count CRTs lists the available CRTCs in the configuration. A CRTC is simply an object that can scan out a frame buffer to a display sync and contains timing and relative position information. CRTCs drive encoders which are responsible for converting the pixel stream into specific display protocol. Okay, so that kind of lines up with what we said earlier today. That lines up with that. And then it looks like they just kind of have them paired like 1-to-1. Okay. Okay. Let's keep going through this guy's thing. So he says, open the thing, get the resources, and now we can check every connector on this card. Connectors. He's checking connectors, which is interesting. Not the CRTCs, which I guess probably makes sense if we're looking for like a specific monitor to write out to. Then that makes sense. And so he's just iterating over these things. He is getting the connector type and the ID, and then freeing that. Okay, I'm down to just copy paste this code for now, just to kind of see what it says. So what is happening here? We called this mode resources. And then he's probably, sorry, is this wrong? Mode resources. And then what's he mad about? Connector type name doesn't exist. That's true. Where is he getting that from? He's made it up. He has made it up. Okay, so where do connector types come from? Uint32T. And where are these like initialized? We could go into build root, libdrm, and we could look in here and see if we can find it. So it was called connector type. So who assigns these things? Con connector type defines a connector. Oh, see DRM mode connector defines. Perfect. Perfect. Wait. No, these ones. All right, let's take a look at these. So I guess we can just write out the value, and then we can come back and check these later. So this is in drm mode.h. drm mode.h. We will try not to forget that. DRM mode.h has defines for connector types. Okay, let's just not do whatever the fuck he's doing, and can we just like print them out? Connector has a type, and what is type ID? Wait. What's the difference between type and type ID? Hold on. Can we open up a second terminal? Maybe that's or a second Vim instance is probably what makes sense here. That has libdrm open. Are you going to do 3D graphics eventually? Probably not today. Yeah, I know that guy has like a GitHub. I didn't want to look at the GitHub from him because it feels like it's kind of cheating. I'm okay with referencing what his like blog post, but I don't want to just like if we just like go into his DRM frame buffer thing, then we will just end up doing no work, right? And so I won't learn as much by doing that. Okay, so let's take a little peek skis at where were we? We were in build libdrm. Okay, we'll just kind of leave this guy open here, and what we're looking for is DRM. We wanted to see what is a connector and what is a connector type ID versus connector type. What is the difference? So we can look for connector type here. Okay. So here we go. This is the type of connector. Type ID is the specific connector number. Right, so if you have like 2 HDMI ports, then you will have HDMI 1 and HDMI 2 would be my assumption here. That would be my assumption. What is this directory selection thing it's using? It's called Ranger. Okay, so connector type D, ID this. So maybe we'll do D:D, and then we'll print out connector type and connector type ID. All right. Make build root and run. He's thinking? I wonder what he's thinking about. Probably just parsing like a million makefiles. This wasn't this slow last time, right? Am I crazy? Maybe it's because we ran with JFlags before. But I'm not sure. All right. So we're looking for test C. Okay. So we forgot to do \n, but we do see that we have four of the same connector type 15 down here. 4 of the same connector type 15. So here we had a DRM mode connector, and we're looking for whichever one of these is 15. Virtual. That makes sense. So he has 4 virtual displays connected to the same driver. I guess that is maybe reasonable. I guess we should maybe assume that we want to use 0. That switch case had an ID string conversion. That is true. DRM mode get connector type name. We should have just done that. Well, for next time. Where does that live? I lost it. It was here. XF86 DRM mode. Okay. We will remember that for next time. Okay. So this guy then picks a specific connector. Connector current. What is that? Get, what is this? DRM mode. Get connector current. Retrieve current information, i.e. the active mode and encoder about connector ID. This will not do any probing on the connector or a remote device and only reports what is currently known. For the complete set of nodes, modes and encoders associated with the connector, use DRM mode get connector. Oh. No, wait, I'm confused. Oh, so he's iterating over all of these things and checking which one is active, I guess. But how do any of them get known? Right? If all of we have done is we've called DRM mode get resources. So DRM mode get resources probably populates this in some way, right? So this is connected. Well, maybe not. If it's just like which one is plugged in and showing the virtual terminal, that's like an option as well. That's an option as well. So this guy calls get connector with probe 0. And here, if we don't probe. Okay, so this goes straight into a DRM ioctal. That's pretty interesting. I would like to know what that is doing. So maybe we open a third terminal and we go into the Linux source code. And can we look for who handles mode get connector? Okay. DRM.h, this looks like it's probably user space API, so it's probably this one is probably the more interesting thing. And this gets matched to some function DRM mode get connector. No client attached? Why? LSP info. Oh, because I'm not in my shell. I haven't pulled in my tools. One sec. He's got to think, he's got to check what is installed and what he has to fetch from the internet. There we go. And let's try again. So we go into source Linux and what was it? It was mode get connector, I think. Yeah. Okay, can we jump to this? LSP info. ClangD is in fact attached. Here we go. Okay. Oh, so this is a input. Okay, so this is from drmmode.h user space API. And he's calling count modes 1. And the modes pointer is he's going out into here, mode info. And oh, I see. No. So if there's no probe, he just asks. So maybe the driver must be holding some internal state. I guess we'll find out. Get connector. So this is just defining the ioctal parameters. Who uses this? Who uses this? Here we go. DRM ioctal def. What the fuck am I looking at? DRM ioctals. Okay. So DRM ioctals, he defines these things, and this sets some sort of function parameter to func. Okay, so on get connector, he is using this function here. Okay. And so here we know that he passed this in with some data here. And in here, he specified that he wanted count connectors. Fuck, what was it? Count modes. To retrieve the number of elements, blah, blah, blah. To set count modes to 1 and set blah, blah, blah. That's not really what I want, I don't think. Count modes to 1 is what we're doing. To retrieve the number of elements, set this stuff. User space is expected to retrieve encoders, modes, and properties by performing this cycle at least twice. The first time retrieve the number of elements, the second time retrieve the number of elements, the elements themselves. So is that what he's doing here? He's calling this get connector current, which came from libDRM. I got lost. So DRM get connector, this comes from here. Oh, and then he calls this once. Then, assuming that this doesn't fail, he continues? Does DRM also return 0 on success or on failure? Probably on failure, right? 0 is returned on success. So this means if this fails, return. Otherwise, we go into this thing. And so then he calls it again. Ah, okay. So this get connector is wrapping the behavior of calling it once to find out how many modes there are. Then he must get the number of modes back. Is that what this says? And set modes pointer to a temporary struct. So he gets the output to stack mode. Ah, okay, yeah, I see. So this then will have number of modes? No? Count to a temporary struct mode info element. I guess we can see what he does in libDRM. Okay, so this just gets set back directly into the input argument, I guess. That makes sense. Then what happens to stack mode here? Also, we were trying to find out where this probe comes from. That was the initial question. So by default, he's calling this with connection kind of zeroed out question mark. Mem clear. What does mem clear do? Mem set 0. Yeah. So usually he's calling this with count mode 0. Unless probe is set, then he says with count modes 1. Oh, but probe in get connector current was unset, if I remember correctly. Get connector current is not probing. Okay, that's another good piece of information. So we are not probing, right? Not probing. So this first get connector is not called with count modes 1. So it's called with count modes 0. If the count modes field is set to 0 and the DRM client is the current DRM master, the kernel will perform a forced probe on the connector to refresh the connector status, modes, and EDID. Ah! Okay. So what the fuck is a DRM? So if I remember correctly, there's something about DRM masters and clients where only one person is allowed to be the master because usually that is expected to be like your window manager. It is setting count modes to 1 since probe is 0. Oh, am I ridiculous? Am I stupid? Yeah, you're right. Probe is 0. You're right. Okay, so he is probing all the connectors. That means that in get connector with connector ID, it's usually set to we are not probing. Okay. Let's go back to this again then. To retrieve the number of elements, set count props and count encoders, set count modes to 1, and modes pointer to a temporary struct. So that means he's not doing that in the normal case. Are these functions documented? Retrieve all information about the connector ID. Retrieve current information, i.e. the active mode and encoder, about the encoder connector ID. This will not do any probing on the connector or remote device. It only reports what is currently known. Okay, that's what I thought. So it almost feels like these are backwards. Based off of the documentation for this ioctl, but maybe we just don't fully understand. Can we look for maybe, how is this called again? He is called with, I guess we don't know yet, but we can assume that the input must be this thing. Right. And then in here, he set the output data to be something on the stack. Stack mode goes to modes pointer. Ah, okay. Okay. So we're looking for usage of count modes in this thing. So if count modes is 0, it looks like it does work. Extra work if it's 0. And that's going to call something connector funcs fill modes. Interesting. Which is probably defined in our like QXL display. Ah, okay. So this guy is probably getting information about what is connected, and probably he stashes that information in the QXL driver. Fill modes, entry point for output detection and basic mode validation. The driver should reprobe the output if needed when hotlog handling is unreliable. Add all detected modes to DRM connector.modes and filter out any device that can't. Ah, okay. The drivers must also prune any nodes no longer valid. So if they don't do this, he's kind of saying that direct connector.modes will already be set somehow. Which means that probably this stuff would have been initialized on DRM mode get resources. That's my guess. Here. I wonder if we can prove that. If we look for the implementation of DRM, I already forgot what it was. DRM mode get resources. So he calls ioctl get resources. Maybe I spelled get resources wrong. Can we just go back here? Get resources. So this guy probably goes for each CRTC. Is there like for each connector? Yeah, for each connector. He does some stuff. Nothing crazy. Are like modes set in here anywhere? Maybe not. Confusing. Connector, it was modes, right? Was what we're looking for? Yeah. So maybe this guy does some extra shit. He does get resources, retry. Oh yeah, okay. So he's only making one ioctl call in here. So then I don't really understand how anybody would have the current mode set. I guess maybe the kernel mode setting will be done on boot. There's like a very real chance of that. Right? I guess we're kind of making it, we're making an invalid assumption that our application is the first person to look at this. But I think that that's not true, right? I think that like when we are booting the virtual machine, we see it resize there. Did you guys see that? It's like small window, big window, right there. So we can maybe assume that there was some sort of like The reason that it's called kernel mode setting is because there's mode setting support in the kernel, right? So we can maybe assume that somebody set it up there, and maybe this example is assuming that it is already set up in some way. That would make sense to me. That would make sense to me. So can we just do, we don't even have to count connectors, right? Oh, we do. Oh, okay. So this is a clever little trick that is happening, right? He's kind of saying like, if the connector has information associated with him, then we must be the connector. Which means that down here, this is where we would want to write down. This would be where we want to write down which one we like. Which one we think is currently connected. I think. We'll find out. We will find out. Okay. We log in. Root. Test C. That's not good. That's not good at all. So those are big ass negative numbers, which kind of indicates that. So I don't know. Oh, we did free it here. Oh, sorry, I was wrong. This prints the current connector. Am I right? He's using tabs here, which are annoying, but that's fine. So here he continues if it was not found. Here, then he does not continue. Okay, let's try it again. Sorry. Sorry. So then we should get one connector printed. Only one, right? It should only print the one that we currently have information about. No, he prints 4. So we have 4 connectors that we actually currently have information about, which I guess makes sense. So he's using cached information. It has nothing to do with if we are, this is what we are currently connected to. It's just printing all our options. I think I understand. Okay. The connector will also tell us what the preferred resolution for the display is. Sure. But how do I know which connector to use? How do I know which connector to use? He is doing something where he is looking for a specific input connector, which he must be getting from like input or something. I know I said I didn't want to look at the GitHub, but here I think that it makes sense. I'm going to try not to cheat too much. I just want to know where that input comes from. So we're looking for his loop on connector name. So he's calling get resolution. So what's he doing? He's doing like I'm printing the connector type and connector ID into this thing, and then I'm trying to check if this is the name that I'm looking for. So here he must be taking connector as an argument. Okay, that's it. Makes sense. So he's got C, connector to use, HDMI A1. Okay. Sure. So we maybe will just assume that we should use the first one. Maybe. I wonder, I guess it kind of makes sense to check what is like Weston doing? How does he determine, when we run a window manager, how does he know which monitor is best? So we can maybe look at like backend DRM is probably KMS, maybe. Oh god, this is a lot of code. Create a backend. Can we maybe look for DRM mode get connector? Okay. So this is in drm.c. He calls get connector and collect new connectors that have appeared. Okay. Then somewhere he must determine. Can you print the names of those 4 connectors you're getting back? Maybe they help understand what's going on. aren't the names just like we said we know that they're all virtual, right? Unless is there a field that I wasn't looking at? I looked at connector type ID. I don't think there is a connector name, right? Oh, I guess connector ID, but probably not, right? How did we do this before? We looked in here and we looked at connector. Oh, we're in libwisten now. Cat sysclass DRM card 0. Oh, that's not a bad idea. That's not a bad idea. CD sys class DRM. Ah, right. So here are our virtual things, and can we like cat star status connected? Ah, okay. Okay, so this is probably the piece of information that we were looking for. Which one of our displays is currently connected? Good eye. Good eye. So where does that come from? DRM mode connection is probably what we're looking for. Nice. Nice. So we can iterate until we find one that's connected and then pick that one. I think that makes sense. So we'll do like if, oh my god, can we set expand tab stop equals 4, shift equals 4, GG equals G. There we go. Hopefully that solves my shit. So we're gonna be like if connector connection is equal to what was it, DRM? It was mode connected. Yep. Here we break. And then we should have a connector pointer that we can work with from now on. And we should be able to say which one of these things is plugged in. So here we'll say, we'll print the one connector that we have found, or well, sorry, not the one, the connector that we've picked. We will say which connector ID it is. And we should see 0. 15:0 for virtual 0. I hope. This is kind of fun. We're learning. I like that we've kind of spent like an hour and 15 minutes to write like 5 lines of code. But this is the process. This is how you learn. You poke and you prod. All right, oopsies. Root and test C. Yeah, so we got 15:1. 15:1. So if we go back to sys class DRM card 0 virtual 1. So it's this one. So we should see card 0 virtual 1. And here we should see status is connected. Nice. Nice, nice, nice. Okay, okay, we're getting somewhere. We are getting somewhere. So now he says, let's try to get the resolution from this thing. Or, yeah, let's look at the preferred resolution. So he is looking over each of the modes in the connector and looking for DRM mode type preferred. Where is that defined? Probably, my guess is the kernel. Yeah, so it looks like this is probably coming straight out of the kernel. And this is defined here. This is in the connector mode output. So in get connector, what was it? It was a get connector here. He set some sort of mode field on this guy. Oh, he just like probably exposed to user space is probably just like a copy to user. Oh, not quite. This is crazy. Oh, so he's checking if we're allowed to send this thing out. If the user space hasn't configured the driver to expose the modes with aspect ratio, don't expose them. Ah, okay, okay, okay. I see. So he kind of filters those things out. Where is this like mode preferred thing getting set? Reset aspect ratio flags if not supported. So these must come out of somewhere else. What was it? It was preferred? Type preferred. So DRM modes.c sounds promising, as well as QXL display. Here we go. Okay. So here we add modes in the QXL display. Where does this called from? QXL display, add extra modes, as well as this thing. Add monitors, config modes. Okay. This is called from connector get modes. Oh, okay. So we probably were getting into this QXL get modes, probably like on initialization, DRM probe helper. Yeah. So on probe, when the question we were asking before of like how does he who initialized this thing? It looks like it's happening like on driver initialization, right? So on we can probably, if we trace this back, we will probably find that this is called just like on every DRM probe. Fill modes, probe single connector modes. Oh, okay, maybe not. Fill modes. All right, maybe not. Maybe I was wrong there. Because it does look like this is just going back to actually the same code we were looking at before. Okay, maybe I was wrong. I've been wrong, and I will admit it. We have to make guesses sometimes, and sometimes those guesses aren't right. Okay, wait, but who sets this guy? It was in QXL display. He says this if preferred. So QXL add mode will sometimes have preferred on him. So this one is unconditionally false, which means that this one is unconditionally true. QXL add monitors config modes, who I forget where he was called, from get modes, which was called get modes. Oh, right, that's where we were. So we kind of assumed that it is. Okay. Yeah. So when this was called by fill modes in that other thing, so when that first get connector call is run, we make it into this QXL get modes, and he set the preferred mode. I still don't really understand where this came from. Connector to p width and p height. So he has some sort of horizontal resolution preferred. And where do these come from? Client monitors config. So maybe like from the QEMU command line, you might be able to specify a resolution that probably gets set into this thing. Would be my guess. That would be my guess. It's kind of hard to tell, but we could maybe look for client monitors config. The first is always connected. Alec client monitors config. Copy ROM client monitors config. Yeah, this sounds a lot like the read-only memory on boot. We set this somehow. So this comes from the QDev QXL device. Where is this constructed? Mode set init. Probably, yeah. So when we probe this thing, when the system iterates all PCI devices, he eventually finds a QXL device. And I assume that on device initialization, he finds a ROM base, yeah, that comes from a PCI resource. Nice. So the virtual element must pass in this stuff somehow. Which makes sense. Can we look for like usages of ROM base? QDev ROM. Yeah, this is looking for like yeah. So he just like remaps some stuff that has all of these parameters in here, such as the desired width and height of the monitor, and then on QXL, when we call that like get connectors, he sets the preferred one to be whichever one matches that width and height. I wonder if we can test that somehow. We could look for like QXL preferred resolution. QXL QEMU command line options. QXL. I think it was like device QXL maybe. I'm pretty sure. I'm like 70% sure I'm right. QXL. Does he have options somewhere? You being able using max outputs, and then somewhere, I'm sure there must be a resolution field. What is XY in the search query? I have no idea where that was anymore. I'm sorry. Resolution. Yeah, I'm not sure. But I'm like, maybe like QEMU set resolution. Okay, I give up. I give up. But I'm like, I think so. Oh, you wrote device QXL. Oh yeah, I was looking for like I know that there are QEMU options where you can specify like device options and then like throw some extra shit on them. I think I had the syntax wrong. Okay, anyways, let's try to find our preferred resolution. So that was from DRM. He was iterating over the connector count modes. So for int I is equal to 0, I is less than this, we should probably use the right type here. So this is int. Okay, we are chilling. We say if connector modes I and DRM mode type preferred. So this must come out of the type in this thing somehow, right? So this is a mode pointer, and he has type is probably what they were doing, right? That's probably what he was doing here. Yeah, he was looking at type. So if this is preferred, we break. And then probably if we get to the end of these loops, we should probably like return. I guess we probably want to put these into functions, both of these things, because we want to be able to detect the case where we did not find anything, right? That's an important failure case here. So let's kind of do this, kind of slap this in a DRM mode connector pointer, get first connected connector. Sure. And he has to get the mode resources, which are going to come from this. So that's going to be our input here. And we also need our file descriptor. And then here we will return connector. And then here we return null. That way we can tell if it's wrong. So we can say equals get first connected connector, FD mode resources, if connector is equal to null, fprintf stood error, failed to find connected connector. Okay. And then we should do the same thing with this modes lookup. So here we're doing like, what is in this? Why is there some break in here? What the fuck am I doing? Okay, so this thing has modes. So this is what we're looking for. Preferred mode equals get preferred mode from FD, probably just the connector like this. And then we have DRM mode info pointer, get preferred mode from their connector. Okay, 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 okay. So here, if we get the type is this, we return mode. Okay. Returning struct, so maybe we have to put a little ampersand on this thing. Makes sense. And we'll do the same thing here. If the preferred mode is equal to null, we say we failed to find preferred mode. Otherwise, we print something interesting about it. So, preferred mode, and then let's like look at like what's in this thing. Let's try maybe just say, okay, vDisplay start and total skew refresh flags type clock. So is HDisplay here? I wonder if this is like the number of clock ticks or if it is the like number of pixels, right? Because this is not. What is this again? This is mode setting on a connector. And according to our diagram in this guy, a connector is like a VGA wire, right? So this feels like parameters for like your number of ticks between things, right? When you see hsync start, hsync end, that sounds a lot like that, but it could also be in pixels. But clock here is like probably a clock ID. It'd be interesting to take a look at that. So we already know that this comes from the get connectors ioctl. Which was here. And can we just look at this thing? And somewhere he assigns this modes pointer. Uh-huh, okay. So he copies this stuff from umode. Okay, yep. And I wanted to see, okay, here we go, perfect. Oh, so HDisplay is the size. Pixel clock in kilohertz, okay, interesting. So I was wrong. I thought it was going to be in clock cycles, but it looks like it's just in pixels. It'd be really fun if it was in like millimeters or something. Just like really fuck our shit up. So it could be that the sync start and end. Sometimes there's like overscan. I seem to remember seeing stuff that's like you have like you can imagine what is being written out to the monitor as something like this, where this is like your like actual stuff, right? You get a little smiley face in here, and then in here you have like kind of like timing codes, so that it knows, like, so that if you have like clock drift between your sender and receiver, they can like look for this pattern and resync up. They can be like, oh, we're at the fucking end of the line, right? Like I could be wrong here, right? But I think this is what's going on. I think. And so this is probably telling us maybe where in pixels those things are. So we could maybe look at the, maybe we print out all of the information. We just printed everything. That sounds interesting. So let's print out the preferred mode. Maybe we say horizontal params, right? Which have HDisplay. Well, I guess we can just kind of copy paste this. Perfect. And we can do a little QQ preferred mode arrow. Okay, and then we'll say printf horizontal params is %d, 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 %d. We should probably put a new line on this thing because it was really fucking annoying earlier. Okay. And then I actually don't know why this is mad. I probably forgot to end my quote here. There we go. And then we kind of do the same thing here. And let's kind of change horizontal to vertical here, and then delete this, join, delete, and align. All right. Sure. Let's see what that says to us. Let's see what that says to us. He's so happy. All right. So here we have 1024 by 768, but there is a start and end from 1048 to 1184 for sync parameters. So what is that? That's 36 pixels. And then there's like a little bit of padding in between here. Right, so 1024 to 48 is empty. 48 to 1184 is timing parameters. And then it looks like the stride of this thing is 1344, so even bigger. So I didn't really look at the skew parameter, which might have something to do with this as well. But we are seeing a 1024 by 768 monitor, which I think lines up with this. 1024 is like a little less than 1080. No, wait, or... Oh, 768, sorry. This is the... 768 is vertical. So like, 5/6 of 1080. I'm pretty sure that's right, but yeah, I was close. If you resize, will it update? No, I think that I need to issue a resize from within my mode setting, and then the monitor will resize according to what I asked for from the virtual machine. I think. Okay. Let's try to get some shit on the screen, though. So here, once he has figured out the resolution, he uses that to create a frame buffer. And he calls DRM octal create DOM into this DOM frame buffer. So, but remember, when we were talking about this before, we thought that the frame buffer was just a collector of scanout buffers. So does he kind of do that does he create a scanout buffer anywhere else? He does create a new... Oh, he just calls map DOM. So where does he like write to this thing? He writes to it right to the frame buffer. So he calls frame buffer DOM frame buffer size, and then we fill it with data from standard in. Okay, sure. So he looks at standard input and he puts that stuff into frame buffer data. Right, okay, sure. That makes sense. So frame buffer dot data must get assigned somewhere from this. Oh, add frame buffer. I don't see any data in here. Oh, here. Here, so he sets the data to an mmap of mrec offset. Ah, okay, wait. Okay, here we go. So he creates another DOM buffer. So he creates one DOM buffer for the frame buffer, and then another one for the scanout buffer, which he sets here. And what is going on here? DRM octal map DOM mrec. So where does he set the parameters here? I'm going to check his actual code again because I am not trusting that he has not missed something. But I assume that mrec must set the same size parameters, probably requesting a specific size in some way. No, he just fucking sends that shit. Oh, here he puts a handle to the frame buffer. Okay, interesting. Oh, and I guess a map DOM is different than a get DOM or alloc DOM or whatever the fuck he did the first time. So he did create DOM, and then he mapped DOM. Create then map. So I guess that the map DOM must use parameters from the frame buffer to create a scanout buffer. That would be my guess. Can we take a look at that? So what was this? DRM mode DRM octal mode create DOM. Who defines this? So this is part of like the generic DRM subsystem. This isn't driver specific at all. And this goes to this function, which calls DRM create DOM. The KMS API doesn't standardize backing storage object creation, leaves it to the driver-specific octals. Furthermore, actually creating a buffer object, even for gem-based drivers. So gem, we saw somewhere, is user space interface to the DRM. Okay, so for gem-based drivers is done through driver-specific octal. Gem only has a common user space interface for shrinking and destroying objects, not an issue for fully fledged graphics stacks that include device-specific user space components. This limit makes DRM-based early boot graphics unnecessarily complex. Nice. DOM objects partially alleviate this problem by providing a standard API to create DOM buffers suitable for scanout. Which can be used to create KMS frame buffers. Right. So this is like real dumb interface. Like, I don't want to figure out the whole graphics stack. Just let me fucking get a buffer, and this is just do the dumbest thing you can. We don't have to be efficient here. So the DRM driver must implement DOM create and DOM map offset. So is this DOM map offset? This is map DOM. So we can see if map DOM, this thing must go into DOM map offset. Nice. Okay. So these things are both probably implemented by QXL. Okay, so when we create a buffer with QXL, we are going to, actually, I guess we should see, is there some sort of like common code that uses this? DOM buffers. So who calls this? Here. So yeah, this is from DRM mode create DOM, like we were talking about just now. And he does a bunch of like argument validation, which in common code, but doesn't actually do any of the actual work. Okay. So then in the QXL, how do we get this thing? What does he do? He creates a gem object, and he sets is DOM on it, I guess. Sure. What is BO? Have you guys seen this container of macro before, by the way? This shit's so whack. It's pretty neat. I mean, we might as well. This is one of my like favorite little C tricks. I think we've talked about it before. But like, if you're gonna do like normal like inheritance, like if you have like C++ and you have like class A inherits from B, right? And then you have like class B has like some stuff in it, right? Like, you know, just like an int x or something. And then in A you can use this like int x. C doesn't have that, right? But what you can do is you can kind of like hand roll your own inheritance, but you kind of like invert this. So instead of you saying like A inherits from B, you kind of have like class A, or struct A, sorry, has a member of B. Remember, B is the like, I guess I should have done it this way. B has like some function, like some generic implementation, right? Like do thing. And then when you like send out B's to the world, and then you have like an implementation do thing. And here you do like print hello, right? Whatever. Here you can still hand out struct B's if they are children of struct A's. But what you do is like, because you know that B is the first member of A, you can just like cast the pointer. Or if you have like an int before here, you can go like, well, B is 4 bytes into A. And so I can like retrieve in like specific implementation details about A by just taking the address of B and subtracting 4. It's like a fun little trick. So is it similar to field parent pointer? Yeah, it's exactly the same thing as field parent pointer in Zig. And so like there's this like kind of like nasty macro in here, but it's basically just doing this like, you know, take the thing and like find the offset of the member in here. You have offset of to do that for you. Yeah. So the container of just like does the stuff for you. Offset of is an extension. Yeah, I think the Linux kernel is totally fine using if I remember correctly, it's not undefined behavior, but implementation specific behavior they're totally okay with using. Right? Otherwise a lot of stuff gets really hard. Like the fact that like macros can return, right? Like this syntax here, where you have a parenthesis, then a what is what this goes? Parenthesis, then brace, means that the last statement in this parenthesis brace will return, which means that you can like do things like this, right? Where I say thing equals this, and then instead of trying to like do while shit, with like a temporary variable, you can just kind of like return a thing from the macro. So like that's not like real C, but it's an extension, and they're like okay using it. Okay, so what we were trying to figure out. So this guy just turns it into like a QXL BXO, which must own a G object inside, right? Because this has a gem to QXL BO, which is base. Oh, so this probably stands for buffer object. Container of GObj. Oh, is it the other way around? GObj has a base field? No, where's this base field coming from? Oh, TBO base. What the? Oh, I didn't know you could do that. That's even crazier. So they can actually get the. So they're going within a member here. They're going like in this field, there's a base pointer, and then we're going from there back to this object. Okay, sure. Who knows what all this means? But maybe it will become interesting to us later, or maybe not. Okay, so this guy creates a thing, and then what I'm more interested than the create function is actually the map dumb offset thing. Right, so the create buffer, I guess I wanted to know kind of like the size. So he creates a buffer that is kind of like this, like this stuff, right? So he goes like, please create me a 32-bit RGB buffer of this pitch and width and height. And is pitch kind of calculated from args width times bits per point? Yeah, okay, sure. So they're rounding up to the size of the element, sure. Or eight chunks of 8 of the element or something like that. Then he creates an object of that size, and then when we map the dumb buffer later, he must just take the memory back out of that thing. Right? He's not actually allocating any memory. Implement struct DRM driver map dumb offset. Provides an implementation of struct DRM driver map dumb offset for TTM based gem drivers. So TTM, I think that's not in our table of stuff, but I did see that somewhere. It's something like there's memory that could be in the GPU memory or paged to disk or paged to system RAM, I think, and it manages the difference between those. Can we look that up somewhere? DRM TTM. Translation table manager. Basic idea is that resources are grouped together in buffer objects of a certain size, and TTM handles lifetime movement and CPU maps to those objects. Okay, I was wrong. So this is like we allocate like 4 things together and they're tied together, is kind of what he's saying. So that makes sense. If you're mapping the frame buffer and the scan-out buffer together, then maybe that's how this makes sense. So he creates some object with false serve. Who knows? Domain CPU. Okay, what does QXL gem object create? So he's got discardable, kernel, alignment, size, blah, blah, blah. So really, this feels like he's just making a buffer of a certain size. Trying to align on a page, sure. Then he makes a QXL buffer object. Okay. And then when we map the scan-out buffer, he gets that thing, right? So he gets the thing that we made, and then he returns into the pointer that is given to us from user space, I assume. We should probably check that. So this is called here. Yeah, so this is args offset, which I think is what he used in his thing. uh, mrec handle data is mmap offset. Yeah. So the offset is where it's weird. Oh, offset is going to be offset from the dumb frame buffer. mmap 0. Oh, from the file descriptor. Yeah, okay. So where within the memory of this file descriptor we're allowed to look at is the dumb buffer written, I guess, is kind of what's being said here. If I understand this correctly, which I might not. Node offset from a VMA node, which he just kind of does like essentially this. Okay, sure. So nothing too crazy. Nothing too crazy. So it looks like the DOM buffer, the scanout buffer, is allocated with the frame buffer when we create it. Okay, let's try that. Let's try that. So here we're trying to fill up. We fill up our frame buffer with the preferred resolution. We say, give me something that can fill the screen. All right. We must need to make a frame buffer, which I assume is just like a... Does he get one of these somewhere? DRM frame buffer. No, he's not interacting with libdrm at this point. He just passes this into... Maybe FB is his own thing, because the ioctl only requests a dumb frame buffer. So maybe we'll just do that. So DRM ioctl mode. Where are our ioctl definitions again? We kind of jumped around here. Create dumb. Right, this is where we're at. So he takes in... Whoa. Do you guys see that? Did you guys know that if you pass a void star into a function that does not take a void star, it just autocasts? That's pretty crazy. So it looks like that we're supposed to use this DRM mode create dumb structure. So here we will say dumb frame buffer. And then probably we want to memset this thing to 0, right? How do you use memset again? Void star int unside long. So this is going to be DOM frame buffer 0 size of DOM frame buffer. Boom. And then here we need like, is it string.h has memset if I remember correctly? Nice. That sucks when you accidentally pass a pointer to void star because you don't get any warnings. Yeah, that's pretty crazy. It's pretty crazy. Okay. And then bits per pixel, 32 bits per pixel. I guess we saw that the options were 16 or 32, and the 32 one gave us an RGB thing, so let's do that. I think that was in the QXL driver code we saw that. And then he just calls, let's fucking see if we can get this thing. So this is going to be our, we'll do if this fails. Fprintf failed to create frame buffer. And we print that to std error. And then we return -1. And he doesn't like this ioctl. Oh, do we need to include sys ioctl or something? Yeah. Okay, and then after that, we should see, like, does this thing give us any outputs? User space fills width, height, bits per pixel, and flags. If the ioctl succeeds, we get handle, pitch, and size. Okay. And then after that, he calls DRM mode add frame buffer. Give him that thing. DRM mode add frame buffer. What does this do? What does this do? Let's go back to libdrm. So this calls DRM octal add frame buffer, and there's really not much here, right? This is pretty straightforward. I'm actually surprised that we were calling a create dumb here. Is there no like? Yeah, I guess not. Create dumb maybe? Okay. They do have a function for this, which does pretty much exactly what this ioctl was doing. So it's probably better for us to use the libdrm version of this function. Oh, that's funny. Iliante asked, I'm probably saying that wrong, but asked the same thing at the same time. Yeah, I agree. It does seem better to just do this. So let's do that. Did I paste this? I did not. Okay, DRM. Fuck. DRM mode create dumb buffer. So this is on file descriptor. We are trying to do preferred mode H display because it was width first. Preferred mode V display. Width, height, bits per pixel. Flags. And then we get out handle, pitch, and size. And are those used for anything? Who fucking knows? He's mad in handle, pitch, and size. And then what are the types of these actually supposed to be? It's uint32, uint32, uint64. Okay, there, like that, like that, like that. Boom, boom, boom. Okay. So this should create this buffer, and then we add, I guess we do if this fails, fprintf stood error failed to create frame buffer. And then I guess that kind of means that all of this stuff goes away. Boom. Okay. Then it was DRM mode add FB. And there's also add FB and add FB2. And I don't know what either of those do, but we can probably assume that these map directly to, we saw it maps to add FB. We saw the implementation somewhere. DRM mode add FB. We saw this calls mode add FB. Okay, so we're looking for add FB here. So what does this do? He does some sanitizing of stuff, then forwards to add FB2, which is probably the newer, better improved version. Then he calls DRM internal frame buffer create on our DRM device. Okay. Somewhere this must make it into, I guess this doesn't necessarily make it into any driver code, right? Because theoretically, this doesn't do anything until we attach the frame buffer to a CRTC, to the cathode ray tube controller. So this could just be like full on just like tracking shit. Adds a frame buffer to the graphics configuration. DRM device, data pointer, DRM. So this must, R is data. So this is the input. Where is like our device used here? Oh, I see. So he makes a frame buffer on the device and then creates the base, the ID of that created thing and puts that to the output. Okay. So here, then he has like a bunch of logs, sure. But what about like, oh, here we go, FB create. This is the interesting part. So QXL actually does implement this. And this, did we see this already? I can't remember. I think we already looked at this, right? So he does a gem frame buffer create. This does not look familiar to me. Oh, because we weren't looking at add FB. We were looking at dumb buffer. Right. So his input here, is the frame buffer ID, the width and height, and pixel format, and flags. Okay. So he initializes something, implementing FB create. This function can be used to set DRM frame buffer functions for drivers that need custom frame buffer callbacks. Okay. Okay, so we have some custom frame buffer callbacks, I guess. Who are our callbacks? Oh, so we're just like get handle and mark as dirty, as in needs re-render. Sure. So somebody probably calls this when we are like ready to swap frames or something. Probably. And this is probably used to flag to like the virtual machine system that like something needs got to happen. Right? We could probably assume this does some sort of like PCI write that the virtual machine like locks onto. Oh, he does just, maybe this just does the actual draw. Maybe, yeah. Not sure. Push command. Not sure, not sure. Okay. But okay, so this does register something. So who he does like a gem in it, and then does this get like attached to the device in some way? Not sure, not sure. Yeah, where does funks get used? That's probably like our clue. That is probably our clue. Ah, okay, so here we go. He initializes some stuff on the frame buffer, i.e. the functions. And then he says, please, can I add this object? All right, sure, whatever. Whatever. It does look like he's doing something interesting. He registers the frame buffer. And then he gets back the buffer ID and the handle. All right, sure. Sure, sure, sure. Wait. Pitch, handle, buffer ID. So did I do the wrong thing here? How come this is... Oh, I don't understand, actually. Width, height, bits per pixel. Width, height... Oh, I missed depth here. And then, I don't know why I typed 0 there. Oh, I copied it from up here, I guess. And I'm just a dumbass. Ah, I'm just stupid. I was halfway through updating this function and I wasn't paying attention. All right. Oops. So it's pitch, handle, and buffer ID. So the buffer ID is the only new thing because we had the handle already from the dumb buffer. So it's like this. Like this, and then we get a frame buffer ID out, which is a what? Unit 32. FB ID. There we go. And we check if this fails. And we'll say failed to add frame buffer. Boom. Okay. And I feel like there's not really much interesting about this stuff, so I don't really think that there's worth compiling and logging again. So let's see what he does next. To show the frame buffer, we need to add it to a CRTZ. That's why we need to get the CRTZ. So here he gets an encoder for our current connector. So we go from connector to encoder to CRTC. Sure. So this is prefer a connector encoder ID. Boom. Which gives us this thing. we say if encoder is equal to null, we failed to get encoder. Okay, and then we can go from there to CRTC. So DRM mode get CRTC from our encoder. CRTC ID, boom. Boom, boom, boom. And then if that's null, we've got another problem. All right. So that's everything that we need. Then he asks to mmap this thing. So this is the actual place where we're going to start drawing stuff. So let's see. They do have a map dumb buffer function in here. So we're going to call this, instead of using the octal directly. And this is from the frame buffer, are like the handle he wants here and the offset, right? So handle, what is handle here? We got a handle somewhere. This is from we're mapping the existing dumb buffer we created. And where was this dumb buffer used again? Nowhere yet, right? Oh, we used it as add frame buffer, right? So we added a frame buffer that is attached to this handle, and then we are mapping this handle. So this handle is like the dumb buffer ID. So I'd actually prefer to call this dumb buffer ID, or even like scanout buffer ID probably makes sense, but we'll call it dumb buffer ID for now. And we are supposed to pass in the offset of something. I forget where that offset came from. Do we have it yet? He got it from, oh, the offset is the output? Yes. Okay. So we'll call this dumb buffer offset. And this goes like this. And this returns a int. So this is failed to map dumb buffer. To map scanout buffer. So this doesn't actually do the mmap though. So I guess this is kind of like prepare scanout buffer mmap, right? So we're kind of saying like, could you please make this available to us in user space? And then now that we have that, we can use that with like a normal mmap call. If I understand what he's doing here correctly, right? He just calls mmap on this file descriptor of this size with the offset. So here will be like dumb buffer data is equal to this. And this is a uint32 star, I think, right? Because we asked for 32-bit RGB data, and we're missing some sort of like thing here. So we don't have this like mrec offset anymore. We just have do we call it db offs? You did. db offs. And this is coming from our DOM frame buffer. What do we call it? We just called it size, I think. Yeah, we just called it size, which is kind of stupid, but whatever. And then we need to get the mmap thing. So this comes from sysmman.h. Okay, big for us. And then I guess probably we just write to this shit. And then we must have to request a resync somewhere. So we write to the buffer by writing fb data, blah, blah, blah. And then he calls set CRTC. Oh, interesting. So he just flips the CRTC on and off. And then he only has the master buffer apply. He only has master mode set during this action, which is fair. All right. So let's just do something like memset. Oh, sorry. I'm in Zig mode, writing at functions. What is the parameters of memset? It's the db data. We want to write this to be like all white, right? So can we do like size times, is size in bytes? I assume size is in bytes. So here we can do like, just fucking like slam that shit with max white. And then we should be able to flip this shit. And then maybe we need to wait a little bit. Probably to make sure that everything is still there. This is the buffer ID, which we called FBID. Let's just double check here. So the thing, it just says buffer ID, but I'm pretty sure frame buffer ID came from add frame buffer. Yeah, so we're resetting this frame buffer for this connector at this resolution. Did we have a resolution somewhere? Oh, we called it preferred mode. And then what is this parameter here? So he's saying set the CRTC to be at this X and Y position, I guess. Maybe you can like have it offset in the buffer. And I don't know what count here is. Oh, it's the number of connectors. So maybe if you're like mirroring displays, you might have several outputs mirrored from the same CRTC, I guess. As we say, put them all to look like this. And then can we just do like sleep like 5 or something? Where does sleep come from? UNSD. Right, because otherwise we will return. I think that this will like if we just exit here, I think that we'll go back to like the console mode. So if I sleep 5 here, I'm hoping that we'll see something more interesting. All right, let's see what happens. Let's see what happens. Give him a sec. He's thinking. Probably disk cache just touched a bunch of stuff while we were typing. And this stuff's got to be reread from disk. Okay, there we go. Run.sh. Let's see. Moment of truth, baby. Test C. Oh, let's fucking go, dude. That actually worked exactly the way I thought it would. That's fucking sick, dude. Is this a big win for us? That's a big win for us. That's actually so fucking sick. Okay, so that we can get a good thumbnail, let's maybe draw something in here. So let's because you know that is the motivation for everything. So let's start by making this thing yellow. So let's assume that this is RGB. If this is like laid out in memory as RGB blank, RGB blank. If we want yellow, that is green and blue yellow? Yeah, I think so. So this would be like this probably. And we can, if we're not sure about which side it's on, then we can also do the symmetrical change because one of these is null bytes anyways. So this should make it yellow, which should give us a little smiley face. All right, sorry, it should give us like the background for a smiley face. And then we can add some eyes and a mouth into the frame buffer in a second. God damn, dude. We have to figure out, if we're going to keep working on stuff like this, we're going to have to figure out a better test setup. This is like when I fucking worked in camera firmware and everybody, when I got there, would always rebuild the entire firmware. And, oh, maybe one of those was alpha. And flash it to the device, which took like 5 minutes. Which I always thought was silly. But just nobody, everyone's like, this is the way we do it. And that pissed me off. And now I'm getting flashbacks. I'm like them now. And I'm pissed off again. But again, this is just not the thing to solve right now in the middle of stream. It's the thing to solve off stream before tomorrow. All right, let's take a look again. root test C. It's white now. That's confusing. What if we take like some zeros out in the middle? Probably what we should do if we want to stop recompiling over and over again. Memset writes by, oh, I'm just a dumbass. Thank you. It's just confusing because it said int as a parameter. But you are right. Is there like a repeated memcopy Linux? Like I want like copy like this sequence many times. Is that like a thing we can do? There's no standard function, sure. But that's fine. That's fine. We'll just do it ourselves. I less than size plus I. Many people on YouTube thinking that so actually call them a dumbass. Yeah, I guess I don't show the chat. So when I'm like, yeah, I'm a fucking dumbass, like I'm saying that to myself, but I guess there's no indication that that's actually what's happening, which is kind of funny. This should be size, I guess, over size of DB data, right? Then we have DB data at I is equal to FF. We said 00 FF 00, right? That's what we said. If one of those is a blank channel and the other one is red. And really, we could make the input a command line parameter so that we could play with colors, you know, on the fly. But instead, we will be really slow and stupid. The classic. It's crazy, like the level of impatience that I have though for this stuff. Like that was like maybe 15 seconds, and I'm like, oh my god, I'm gonna lose my mind. Okay, yellow. I am too small, which is kind of funny. Because I did size of DB data, not size of star DB data, which is double the size. Thank you. Yeah, you caught it at the same time as me. I want to say that although two of you typed that in chat, I got there first. I just want to say I didn't see. Maybe my peripheral vision can read, but I don't think it can. So I just want to be clear. I won that race, but just by a little bit. Okay, and then if we want to draw some like eyes in the middle, we have like we have like what width. Where did we define widths? Do we just write it down? Preferred mode H display. This is the width. Over. How are we gonna do this? I guess we'll give him some eyes that are just rectangles in a couple places. So for maybe this, and we'll kind of assume that his eyes are at 1/3 and 2/3 into his face. Yeah. So maybe we'll make a little like draw rect. And he's going to take in the unit 32T data. And we're going to say at we're going to have taken a width as well. And then we will say that we want it at x1, y1 to x2, y2, I guess. Okay. And I guess we also want a color. Okay. And that's going to look a lot like this loop. So stupid. Why am I copy pasting this loop? So for y is equal to y1 to y is less than y2 plus y. We do the same thing for x. Then in here, we set data at, we have like pixel pause is going to be y times width plus x. And then we have like, oh wait, that's fine. So we don't need to limit this at all. We just put this in pixpause. The size conversion was only because we didn't know how tall the thing was, which is fine. And then here we set the color. Do I need width or stride there? The frame buffer. Ooh, that's a good question. That's a good question. It does feel like it should be stride, huh? It does feel like it should be stride. So for those of you who are like, what the fuck is a stride? Kind of like generally, if you ask for a buffer that is not like, there's going to be like some like hardware multiple of bytes that it's going to want to store as like one row so that you can get like accelerated access. And so typically if you ask for something that's not quite that, then you'll just kind of have like a bunch of like data on the right side of your buffer that's kind of like useless. And so that's like, this is going to be width and this is going to be stride. Or sorry, this whole thing is stride. And so I think you're right that it should be stride. I think you are right. I didn't see that anywhere though, which is why I'm kind of surprised. I guess somebody gave us a stride output, or they called it pitch here, right? So when we created dumb buffer, they output a pitch, which is the like actual thing. So we're gonna draw something into DB data. We're going to use pitch here. And then we're going to do like preferred mode H display over 3 minus. Okay, let's call it like, we'll make some constants here. We'll say like, oh, you went 64T. I don't remember what the, we'll look at preferred mode H display. What unit is this? This is uint 16. So uint 16T width is going to be like this over 10. Let's make an eyeball that's 1/10 the size of the screen. Okay, and then we'll call this center is this over 3. We'll call this left center is this. Okay, and then now we have left center X, I guess, and Y is going to be the V display over 3. Do I kind of want it centered in both horizontal and vertical? Fuck it, why not? Okay, then here we do from X1, Y1. So this is left center X minus width over 2, left center Y minus width over 2, because the width and height are going to be the same. Okay, then we have X2, Y2, which is just the same thing, but plus. Boom. Wow. Wow, and then a color. So 0. Just make it black. And then we're gonna do this twice because we're also gonna have a right center X, which is gonna be left this times 2, I guess. And I guess center Y is the eyes are going to be at the same height. So left center Y is actually going to be I center Y. And then let's give our little smiley face a mouth as well. So we're going to make him kind of like unamused. We're going to make him unamused. And so we're going to have the mouth center Y is going to just be the I center Y times 2. That seems reasonable to me. So that's going to be mouth center Y. And then the X is going to be from the left center X minus width over 2 to the right plus width over 2. So we're just going to make the mouth of him kind of like line up with the sides of the eyeballs because we're being fucking lazy. And then I think that should kind of do what we want it to do. Maybe. There's like a non-zero chance that this gives us a little smiley face. Or I guess he won't be very happy. A kind of little unamused face. We shall see. And this part is very unimportant, but it needs to get done. It needs to get done, even though it's not important for my own amusement at this point. All right. Run. And let's see if it did what I want. Instead, we segfault. We're probably going out of bounds of our thing. So we were probably fucking this up in some way. Probably. It would have been nice if we kept the logs, but I'm almost positive that we are doing something stupid here. Probably actually wants width there instead of stride. I mean, we could find out. I suspect that that is not the case. Oh. Why is width only defined for the first time here? That's actually kind of surprising. Can I call this eye width? Because it feels like that should conflict with something, but it doesn't. Seems like it wants pitch there. I guess no, because the M map, if the M map is directly mapping the buffer, stride makes more sense. Can we log stride here? Pitch is this, width is this, size is this, and let's get height as well while we're at it. Is pitch in bytes or pixels? Yeah, we've got so many questions here. Pixels would make sense as well, right? So where is our width and height defined again? Those are from the mode. So that's here, v display here, v display, and then we had the size was size. And then size wants to be LU probably. No, LU. There we go. There we go. Give him a sec. He's thinking. I think that actually, like, the slowest part here is makefile parsing, I think. I'm pretty sure I've seen that before. We're in, like, large makefile projects. Like, the time to just, like, figure out the build rules is more than the time it actually takes to build stuff, which is kind of funny. Test C. So we have pitch is 4096, width is 1024, height is 768, and the size is 3145728. So let's pull out the calculator. And let's just do a quick 3145728 over 768 is 4096. So pitch is in bytes. Pitch is in bytes. So we need to do stride over size of data. Right? If stride is in bytes, then we turn it back into pixels here. And we should assume that the stride is always a multiple of the pixel size. And if that's not true, then like get fucked. I guess we should just do like assert stride percent size of data equals 0. Because, you know, if we're going to be good citizens of programming, we should at least check our preconditions a little bit. Because I'm actually not 100% sure that's true. In which case, then maybe doing this as like a UN32 pointer is like a kind of fucked. But I don't see it in like any reasonable sense. I would be very shocked if it wasn't 4-byte aligned. Like, that would be crazy. Fuck. Probably because we actually turned off the yellow memset. We just forgot about that part. We did just forget about that part. So, memset db data. I guess we just do another draw rect because we deleted our loop. So we'll go from 0, 0 to preferred mode, H display to preferred mode, V display. And here we had to set to yellow. Oops. sometimes it's easy to make stupid mistakes. I guess the idea that this is for the thumbnail is actually just untrue as well. Because the thumbnail I was going to write, do a little like include DLFW, no. And then open dev DRI, yes. I think that's a better thumbnail. So this is really just for us. Oh my god. Wait, it's actually so sick though. That's actually awesome. We fucking did it. We fucking did it. Look at that. Look at that. All right. Sick. That's actually pretty sick. Okay. So we got some information, not a lot of information, right? We kind of have just done like the very basics of how the fuck do we use the DRM subsystem to draw stuff on here. We did a little bit of looking into like libDRM and a little bit of looking into the kernel driver that is being used here. So we have like a better picture than we did at the start of the stream, but there's still a lot to go, right? So pretty cool, pretty cool. Yeah, I think we call it there. That's a nice little wrap up. So thank you for watching, guys. If you liked what you saw, we stream most days at 12:30 Pacific time to 4 o'clock Pacific time. 12:30 to 2 is kind of like happy hour, where we do kind of like no new features, but like we're minor features or cleanups, or just like kind of like hangouts, do some research, stuff like that. And the 2 to 4 segment is this segment that you are seeing now. If you're watching on Twitch, all of our VODs are on YouTube. The happy hours get archived to member YouTube, YouTube member VODs or Patreon. So if you want to see those are there. If you're watching on YouTube, swing by on Twitch if you feel like it. There's a Twitch link in the YouTube description. There should be a GitHub link in both. I have not made a project for this yet, but we will probably make one. I think I don't get why the yellow draw works correctly. I thought you call it with width instead of pitch. Might have seen it wrong. I think that we used size for the yellow draw initially, and then here we are using the width and height for the size that we want to draw, but the pitch for the stride of the Y thing, right? So like we're specifying that we want to draw like width and height yellow, but then in order to calculate Y, we're using the pitch. Okay. Okay. I think that's it. Like, subscribe, Twitch Prime. And let's say goodbye to YouTube, and Twitch, let's raid somebody.